So for our retrospective power analysis, we want to know how much power does my study have. All of the study has been done. You know what the actual observed effect size was because there are presumably two groups, or if there was only one group that's being compared to a null hypothesis distribution, you know the characteristics of the sample as well as the null hypothesis distribution, and you can figure out the difference between those two distribution means and calculate their standard deviation. And those two factors let you calculate its effect size. And since you know the sample size of the given study, you can compute the power. The prospective power analysis begins with a decision about what is a desired level of statistical power that you want for the study. And with that desired power in mind, you make choices about what assumptions you are making for the study. And based on those assumptions, the key question is, how big of a sample size do I need, given these assumptions, to get a certain desired level of statistical power? As I mentioned, when you're doing your own research, you always want to do a power analysis, prospective power analysis, before you have done the study, because you never want to be in the position of analyzing a study you've already done and concluding, wow, this study was underpowered. And I mentioned in this definition of our prospective power analysis that we often want to achieve a desired level of statistical power. So what is that desired level? Well, just like lots of other things we've encountered so far, this desired level of statistical power is agreed by convention to be a minimum of 0.8. So 0.8, which we often talk about as 80% power, it's considered the minimum power a study must have for the study to be meaningful. So you guys have saw me reference this quote from a famous statistician saying that an underpowered study ought never to have been done, because an underpowered study is so difficult to interpret that it doesn't give you any information regardless of the outcome. If you fail to reject the null hypothesis of a study that has too little statistical power, you're not really confident that the null hypothesis was in fact true in the case of that outcome, because if it is low statistical power, even if the null hypothesis was false, there's a very low chance that you would end up rejecting it anyway. And for today, we're going to continue using the Shiny app for statistical power, but I will also demo to you this program called gpower, a free software. It's a lot simpler to install than any of the softwares we've had so far, so don't worry about that if you had trouble with prior softwares. And I'll have you use this, which is really much, much simpler than the interface might originally seem to show, for calculating power. Essentially, it is a much more powerful, non-internet dependent version of the statistical power Shiny. I'm pretty sure that both of them run on the same kind of framework, and that the Shiny app was designed based on gpower. And under here, I gave you the symbols and the equations that'll be useful for power calculations. And I think the best way to show power calculations and the different ways that factors like sample size and effect size and choice of alpha value affect the results is to do what I did last time, which was simply have pencil and paper and together go through some examples where by changing one factor at a time and then doing the calculations, seeing how that change in one of the parameters like sample size or effect size propagates out and ultimately affect statistical power. All right. So once again, we have power equals 1 minus beta. So can anyone tell me what beta was? So beta is the type 2 error rate. Where a type 2 error was something we had previously called a false negative. And the best way to visualize what a false negative means is to go to that 4-quadrant model that we first learned about in chapter 5. There it is. So if you recall, we have this model. This 4-quadrant model represents the 4 possible states of the world after doing a statistical test. When you do a statistical test, like a null hypothesis significance test that has 2 outcomes, you either reject the null hypothesis or fail to reject the null hypothesis. Those are the 2 columns in this 4-quadrant model, the conclusion you draw from your statistical test. So there's only ever those 2 options for a null hypothesis significance test. Similarly, there's only ever one true state of nature or true state of reality. Either the null hypothesis is true or the null hypothesis is false. And our statistical test can either come to the correct conclusion or an incorrect conclusion. If you fail to reject the null hypothesis and the null hypothesis is true, you've made the correct conclusion. Similarly, if you've rejected the null hypothesis and the null hypothesis was in fact false, you've also come to the correct conclusion. But then there are 2 kinds of incorrect conclusions that are called type 1 and type 2 error. Type 1 error, which is represented by alpha, the rate of type 1 error, is a false positive. You reject the null hypothesis, but the actual state of the world is that the null hypothesis is true. As a result of either random factors or experimental error or poor sampling procedures, you have come to the wrong conclusion. And if you were to publish your results, you would be propagating false information into the world. So type 1 error rate is very important, and we always want to minimize type 1 error. But here, for the sake of statistical power and its calculations, let's look at type 2 error, where you have failed to reject the null hypothesis. However, the null hypothesis is false, and all things being equal in a perfect world, you would have rejected it. So statistical power is only looking at this bottom row of this 4-quadrant model. This is a way of explaining it that came to me pretty recently, but I think it's pretty good. So statistical power is only interested in a world in which the null hypothesis is false. So this is something I encourage you to write down. I don't think I wrote it down anywhere so far, but this is something I think will help you understand what statistical power means. If you understand this 4-quadrant model and the different types of decision errors that can take place, understand that statistical power is looking specifically at this bottom row where either you come to the correct conclusion and you reject the null hypothesis, since that's what's true of nature, or you come to the incorrect conclusion and fail to reject it. What statistical power is interested in is if the null hypothesis is false, what are the chances that you will get a type 2 error or come to the correct conclusion? And statistical power means if the null hypothesis is false and you do a study of a certain parameters, such as certain sample size, certain standard deviation, etc., what percent of the time would you come to the correct conclusion? Which is to say, what percent of the time would you reject the null hypothesis in that situation? And if the percentage of time you would reject the null hypothesis if the null hypothesis was in reality false is very high, let's say 99% statistical power, that means that 99 times out of 100 that you did a study of those parameters, you would come to the correct conclusion and you would reject the null hypothesis, which is the correct state of the world. But if you have low power, let's say your power was 20%, that means that only 20% of the time that the null hypothesis is false, you would come to the correct conclusion by rejecting it. So that's just an illustration of why statistical power is so important. Because if the null hypothesis is false, your research hypothesis is true, you want to be able to reliably come to that correct conclusion. But if your power is low, you can't. So this is why power and type 2 error rate are in this kind of inverse relationship. So if you were to draw them as a pie chart, let's say that you had 80% power. When you have 80% power, that means power is 0.8. And if you know power is 0.8, you know that beta equals 0.2, or 20%. This is roughly correct. So you always want to be in this situation where if you do a study with a certain level, with certain parameters, you always want the power to be very, very high, because just by random sampling, you want to be able to detect a real effect if it's there. So by contrast, if you have the reverse situation with 20% power, and in the situation beta equals 0.8, your power is the smaller slice of this pie chart. And if you do a study, there's an 80% chance that you'll make a type 2 error if your research hypothesis is true. That's really an unacceptable amount of error. And if you only have a 1 in 5 chance of actually finding an effect that you expect to be there, it's really, those are not good odds. If this were a gambling game, you would never want to bet on 1 in 5 odds, whereas you would want to bet on 4 in 5 odds. So now let's look at some simplified examples where we vary aspects that can affect power, and by varying those aspects, see how power changes. And we'll look at 2 different situations. One, an existing study whose power we want to evaluate, and then we'll move on to designing a study. All right, so let's make a very, very simple study. Hold on. all the times to forget how to use this program. I know that I'm going to take longer to remember how to undo that file select tool than to actually just reopen the program. There we go. Goodness. All right, I'm not going to try to mess with any other parameters here. I use this program all the time. All right, that's good for now. All right, so let me give you some fake data about a hypothetical study. Let's say that we're doing a z-test style study where we have a sample mean, and we are comparing our sample mean to a null hypothesis. Let's say that our null hypothesis predicts a mean of 100. And let's say that our sample mean was 120. So this null hypothesis distribution predicts 100, and our alternative hypothesis was 120. So we're not sort of predicting 120, we actually, in this example, found 120 to be the correct result. I need to zoom this out after all. Oh, that's right. All right. And let's say that for both of these distributions, let's assume they're normally distributed, and let's assume that the standard deviation is known. And the standard deviation is, let's say, 4. Actually, let's make that 7. So this looks fairly familiar. Doing these sorts of problems, we're likely to get distributions that look like this. So let's also hypothesize that for our sample size, for the mean representing our alternate hypothesis distribution, I'm just going to highlight the fact that this second mean for our alternate hypothesis was based on a sample mean of 120. And let's say that we had a sample size of 10. And let's say that for this particular study, we had an alpha value set at 0.05, which is the common alpha value we've seen thus far. And let's also say that for this particular example, when we're comparing these two distributions, we wanted to do so with a two-tailed test. I'm just going to write at the top that this is a retrospective power analysis. So in order to figure out what the power of this study is, you could take all of these assumptions and simply go into the, go to the textbook and look at their series of steps. I don't recommend doing that when the Shiny app exists. But one thing that I just wanted to highlight is that this standard deviation here, if you were to go from this standard deviation and put this standard deviation of the population distributions into the Shiny app, you would not get the correct answer. When you go to the Shiny app, you have to convert this standard deviation, which is for the population of scores, into the standard deviation of the mean. So that's mu subscript m, or SEM. And that was always given to us by the variance of the distribution of scores divided by the sample size, which in our case would be 7 squared, or 49, divided by the sample, which was 10. So we have 4.9. So right now, we have enough information to go directly into the Shiny app and figure out the power of this study. But the Shiny app actually does something for you that I want to actually do explicitly here, which is calculate the effect size. So the Shiny app asks you for like the values of the two distributions, their means and their standard deviation, even though it says standard deviation, but they mean standard error of the mean. Just keep that in mind. So let's actually calculate the effect size for this particular problem. So the effect size is given by D equals mu1 minus mu2 divided by the standard error of the mean. So it says standard error occasionally, but because we're dealing with distribution of means, we have to do it by the distribution of means. We have to do it by the standard error of the mean as the denominator rather than the standard deviation alone. So mu1 and mu2 are given here. We have 100 minus 120 divided by 4.9 and 20 over 4.9. I cannot do that in my head, hence Excel to the rescue. It's about 4.1. So once again, I've chosen a very, very extreme example of a study that is very unrealistic. So if you remember the conventions for effect size, we have the small effect size being around D of 0.02, the medium being around D of 0.04, or sorry, 0.06, and the large being around D of 0.08. So when you have a value of 4.1, that is what we in the business would call a crazy value, an impossibly high effect size, but don't worry about that for the sake of these calculations. So let's go to the Shiny app. So the Shiny app is going to tell us the power of a study with these properties. So all of the information that I gave you in that handwritten stuff, I can simply include here. So the type of tailed test, this is our two-tailed test. This is just toggling which of the displays to show, which distribution to show. It doesn't matter for the calculation. It gives us several options for alpha values. And the alpha value of 0.05 is pre-selected, and that's the one we chose for the problem anyway. So the null hypothesis mean was 100. The alternative hypothesis mean was 105, just here, but ours was actually 120. And also, to my surprise, they actually, I forgot that they actually do specify standard error of the mean as the parameter they want here. So I thought that I had to emphasize that, but it's actually right there. I just forgot. But we found that this was about what was it again? I think it was 4.9. Let me just double check. That's right. We calculated it to be 4.9. All right, so what we have included here is all of the information we need to calculate the power. So the fact that the effect size turned out to be an insanely high number relative to what we consider to be reasonable effect sizes in most studies is reflected in the fact that with a study of these qualities, the type 2 error rate is given here as 0.016, which is about 1.7%. So if beta equals 1.7%, what is the statistical power of a study with these characteristics? Yes? Sorry? Is the power small, or is the, so what is the power? So what is the relationship between power and beta? So power and beta are inversely proportional. So if we want to calculate the power, knowing that beta is 0.017, let's see what that looks like. So if from the Shiny app, we find that the type 2 error rate of such a study is 0.017, that means that the power is going to be 1 minus beta. So 1 minus 0.017, I believe that equals 0.983, or 98.3%. Why am I writing this so small? So a study with 98.3% power, if we were to convert that into our definition of power that we learned about in the lecture, it means that in the event that the null hypothesis is false and the research hypothesis is true, you will come to the correct conclusion and reject the null hypothesis 98.3% of the time. That is a very, very acceptable rate of error. If you did a study and 98.3% of the time you came to the correct conclusion, which is to say your conclusion matched reality, that is incredibly, that's amazing. And like I said at the beginning, the general convention holds that as long as your statistical power is greater than 0.8 or 80%, that's acceptable. The fact that you can get the power here is 98.3% is way higher than the minimum that's considered acceptable for most studies in social science. All right, so once again, let's do the same problem, but I'm just going to modify it a little bit so the result does not come up to such a crazy high value of the standard error. That's a crazy high value of the effect size. One of the reasons why I want to choose a kind of problem where the effect size is more typical is that if I was to do a study and I calculated an effect size of 4.1, my first thought is I've obviously done some calculation wrong earlier in the process. And so I don't want you to have the same kind of issue where, or I want you guys to just recognize that 4.1 is not a reasonable effect size in most situations. So let's actually change this from 105 to 105. So this is great. Now that this is 105, but everything else is being held equal, we can go, what am I doing? Huh, I didn't realize that would happen. All right, so now that I've changed that the second mean from 120 to 105, we can go ahead and see how that affects the statistical power. The statistical power where the difference was 20 points instead of 5 points resulted in 98.3% power. It also resulted in an effect size of 4.1. But if we were to change the mean of distribution 2, we would actually end up with an effect size that is much smaller. The effect size here would still be a very large effect size. It would be approximately 1, which is considered very, very close to a large effect size, but it wouldn't be the crazy one of 4.1. But let's go ahead and see how choosing 105 as our sample mean changes. So the only thing we'd have to change for the shiny app is the alternative hypothesis mean from 120 to 105. Doing that results in a beta value of 0.82. So if beta is 0.82, what does that make the power for this study? So if beta is 0.82 and power is 1 minus beta, we know that the power is going to be 1 minus 0.82, which is approximately 18%. And if power is 18%, it means that if you did this study, you would only reject the null hypothesis, which is the correct conclusion, 18% of the time. That's crazy results. Those are crazy odds. I would never take those odds. And in such a situation, you would not even want to have done this study in the first place. Because if this study is so unlikely to come to the correct conclusion, even if the research hypothesis is true, you might as well have just done another study or designed your study differently, or in most cases, gotten a larger sample size. All right. So what I'd like you to do now is I would like you to open up your laptop or your phone, open up that Shiny app, and I want you to see what happens when you change the standard deviation from 7 to 15. So I'll give you guys 2 or 3 minutes for that. All right, so what did you guys get as the statistical power when the standard deviation of the distribution of scores was 15 rather than 7? So when you change, oh, yes. Did you say beta got larger? So that is correct, but how does beta getting larger affect statistical power? There's always a relationship between beta and power. As one goes up, what happens to the other one? Yeah. So whenever beta increases, power decreases. And that's actually always going to be true. Well, actually, hold on. Let me actually, hold on. Forget I said it. Let me just make sure that I understood what I was asking you correctly. So if you increase, okay, so you're correct. Sorry about that. I was looking at the wrong thing on the page. Yes, by increasing the standard deviation, which increases the standard deviation of the mean, what effectively that means is there is more overlap between the two distributions because there's more variance in each of them. And if there's more variance in each distribution, the effect size is going to be smaller because of the formula for Cohen's d, which divides by the standard deviation term. And that in turn affects the power calculation. But let's actually see this in action. So if the standard deviation was 15, that means that the standard error of the mean calculation, which is going to be the standard deviation squared divided by sample size, but instead of 7 squared, which it was before, we instead have 15 squared. And I believe 15 squared is 225, but I can't recall. Yep, 225. So 225 divided by 10 gives us 2.25. And if we have 2.25 instead of 4.9, that means that when we're calculating Cohen's d, let me just put in 105, which was our original value. Oh, hold on. There's a question from the chat and a question in class. Oh, thank you. It's 22.5. Sorry about that. Was that your question as well? Well, yes, the standard error of the mean is 22.5. Wait, hold on a second. There's something wrong here. 15. Oh my goodness. I made a mistake earlier on. Is it because, are you going to say I didn't take the square root of the standard error of the mean? Oh gosh, I'm so sorry. I need to make an annotation in the YouTube video here. All right, so the standard error of the mean is not this formula. It is the square root of this formula. Oh gosh, sorry about that, guys. So this should not be the square root. This should not be 22.5. It should be the square root of 22.5. I'm so sorry. All right, I'm very sorry about that. So this is about 4.1. I recommend that you go back and try doing the original without this error, because this error is pretty consequential. So make sure that when you're doing the standard error of the mean calculation, you actually don't make this doofus mistake that I just did. And if you do it correctly, you end up with 1. This is approximately 8. So this is approximately 0.8. So even though this error was for this calculation of Cohen's d, and the calculation of Cohen's d before was a huge overestimate, in large part because I forgot to take the square root of the standard error of mean calculation. But in terms of the Shiny app doesn't ask you to calculate Cohen's d, so it actually got the correct answer. So in terms of this lecture, there was an error, but this error only affected the Cohen's d calculation and not the results from the Shiny app. So going to our Shiny app again, with our now correct standard error of the mean of 4.1, let's see what we get. So all other things being equal, standard error of the mean 4.1. So in this circumstance, we have about 77% rate of type 2 error. Remember, for 77% type 2 error, that means a power of only about 23%. And since the minimum power we want is 80% or 0.8, this is unacceptable. And if you were to observe an experiment that had these properties, you would say this experiment should never have been done. And this is all leading up to the last example, which is what happens when we affect the sample size. So here is this, we've just been looking at a study where the power is way too low. But now let's change one thing about the study. Let's change the sample size of the mean that we collected for our sample mean. So here, our sample mean was 10, but let's actually see what happens when the sample mean gets changed to 50. So take 2 or 3 minutes to go through the problem and use the Shiny app to figure out what the beta will be and what the statistical power will therefore be for a problem with the same parameters. Just to make sure 105 is here. Everything is the same, except the sample size is 50 instead of 10. And pay attention to whether changing the sample size, in this case increasing it, decreases statistical power of the study or increases statistical power of the study. That, to me, is the most important thing to communicate to you, the relationship between sample size and statistical power. All right. So by changing the sample size from 10 into 50, if our goal is simply to input this into the Shiny app, the only thing that we have to calculate is how this affects the standard error of the mean. And essentially, all that will be affected is the denominator of what's inside the square root function. So instead of dividing by 10, we're dividing by 50. So 225 divided by 50 will be so 225 divided by 50 is 4.5. So we're going to take the square root of 4.5. And that gives us 2.12. So we have our standard error of the mean of 2.12, and everything else in the problem is going to remain the same. So let's change this from 4.1 to 2.12. But before we do that, just pay attention to what it says in the plot for beta. Beta is 0.77, just about, which means statistical power is 23%, unacceptable. But by increasing the sample size from 10 to 50, we see that beta is now 0.345, about 35%. So beta has gotten considerably smaller. And because beta is now 35%, power is now 65%, which is not yet at that 80% threshold that we want, but it's still better. If you were to do a study, it would be more likely that if the research hypothesis was true, you will actually come to the correct conclusion. So notice that by increasing the sample size, we have gotten closer, we've increased the power, and we've gotten closer to our desired power of 80%. And these examples so far have looked at studies that have already been done. The two distributions and their means have already been calculated. The standard error of both distributions is calculated. But let's say that we were doing a study where we were designing it from scratch. We don't know the effect size because we don't know the observed effect size because we haven't done the study yet. But we do have, and we also don't know the sample size because we're still in the phase of designing the study, and we have to choose in advance what sample size we want to get. Often in studies, the idea is to choose a minimum sample size in order to get a minimum level of power. But if you get more, if you have a higher sample size than you need and your power is greater than 80%, that's great too. 80% power is not like a sweet spot, it's a minimum standard. And if you can get higher power, all the better. So what if I were to ask you, for a study like this, what would the sample size have to be in order for power to be at least 80%? Let's say that for a study like this, let's say that in advance of picking a sample size, we know that we want to do a two-tailed test. Let's say that we know that the null hypothesis mean is going to be 100, and we know we're going to choose a 0.05 error rate for our type 1 error rate. What are the things that would affect statistical power? So I already mentioned sample size. So which one of these buttons on the Shiny app does sample size affect? Does it affect either of our two means? Does it affect the standard error of the mean? Yes. Yes, exactly. The sample size affects power by affecting the standard error of the mean. And that's because the standard error of the mean calculation divides by the sample size. So because the standard error of the mean calculation requires you to divide by the sample size, and small standard error of the mean increases power, by increasing your sample size, you are shrinking the standard error of the mean, and by shrinking the standard error of the mean, you are increasing your statistical power. That is the sort of two-sentence summary of how sample size affects power. Though it's usually sufficient to just say, by increasing the sample size, you increase power. But if you wanted to know why, from a mathematical point of view, it would be through that standard error of the mean calculation. So before I show you how to do this calculating-wise, we can actually just, it's called brute forcing it, or trial and error, I guess. So what if we change this from 2.12 to 2? So by changing it from 2.12 to 2, the beta rate is now about 29%, whereas it was 35%. Let's lower it to 1.8. So by lowering it to 1.8, the beta value is now close to 20%. And remember, when beta is 20%, that means our power is 80%. But because our beta value is slightly above 20%, that means that if we want a minimum statistical power of 80%, we actually have to decrease beta a little bit more. So I'm sure that if I go to standard error of 1.7, suddenly now beta is 0.16, or 16%. And power is therefore 1 minus 0.16, or 84%. So what we can see here is that in order for a study that has these kind of properties, two-tailed test, alpha of 0.05, a predicted difference between our null hypothesis and alternative hypotheses of 5 points, we know that the standard error of the mean has to be between 1.7 and 1.8, probably a little bit closer to 1.8. In reality, or in general, calculating what the desired sample size is not something you would ever do by hand. The reason why it's even possible to do this by hand is because we have made a lot of assumptions and simplified the problem pretty tremendously. But this kind of brute forcing solution is typical of what researchers actually do when they're trying to plan in advance what sample size they should have. So let's say that for a sample size of 1.7 is the minimum standard error of the mean of 1.7 is the value that we want to achieve. In order to get a standard error of mean of 1.7, what sample size would we need? So let's go back to our Autodesk Sketchpad. So what we're trying to figure out here, we now want to figure out what sample size do we need for power equals 0.8. And we found, more or less empirically, through the Shiny app, that the standard error of the mean would have to be 1.7 in order for the power to be 0.8, all other things being equal. Let me just erase this. So we're trying to find our sample size. And we're trying to find a minimum power of 0.8. And we know that our standard error mean for a power of 0.8 is about 1.7. And our equation for standard error of the mean, remember, it's the variance divided by the sample size. So if we want to find the sample size, we would do it like this. Well, it's not too important, but I don't want you to have to focus on the mathematical aspects. I just want to show you this as a demonstration. And then I'll have you do the in-class assignment. But to figure this out, you would just square both sides of the equation. So 1.7 squared. Hold on a second. I need to go back to the Shiny app to make sure that I have this. I don't want to take up too much time, so I'm just going to tell you that the result is going to be that the average, the sample size that you need is close to, it looks like n equals 90. So this is fairly surprising because a sample size of 90 is a very, very large sample. And this is actually fairly typical. Most people, including most trained statisticians, radically underestimate the sample size that's necessary to actually get a minimum statistical power. So this actual sample size calculation, I actually thought that it would be very straightforward to do given the simple assumptions here, but it turns out it's not without the software I was using, GPower. But you will learn how to use GPower to get this in a matter of seconds. Apologies about that. But having a very, very large sample size as a result of a power analysis for getting a specific level of power is very, very typical. When I do a sample size calculation for my own work, I am always absolutely appalled by what sample size is required to see a particular effect, even if I think the effect is going to be very large. Like, let's say I'm looking at the effect of some drug that has been previously described as being really, really detrimental to like cognitive performance in a rat. And I predict a large statistical effect. And I'm planning a sample size based on a large statistical effect. The result of the power analysis is very often you need like 120 subjects per group in order to find a difference with a minimum level of power. And in most cases, when you're doing an experiment that gets, when you're planning an experiment that has very small effect sizes and you want to compare many different groups, often the problem is that you were way too ambitious in the kind of experiment you wanted to do. And what you should instead do is, instead of try to do an experiment with low statistical power, is you should instead try to cut down your experiments so that you don't have quite as many groups to compare, or you don't, you sort of make the experimental approach kind of more extreme in order to predict a larger effect size. So often these effect size calculations, the intention is not to kind of discourage you from doing any experiments at all. It's to discourage you from doing very, very ambitious experiments. So that's just something I wanted to communicate with you guys. So for the rest of the class, I want you to take out your in-class assignment and answer those questions. I'll turn on the lights. For those of you who are here by Zoom, I've posted the in-class assignment. Just open it up on your computer, and when you're done, send it to me by email. Yeah, I really thought that I'd be able to figure out how to calculate the sample size here. But you can't. There's an assumption here that G-power must be kind of doing some kind of complex statistics to figure out. Interesting. Yes. Yep, that's 100% fine. Yes. I'm sorry? It's fine. We're just on the way. I'll pick it up for you. the opportunities to take class from it. All right, guys, for those of you who are still on Zoom, please send me your in-class assignments via email. And have a good day. I've been recording this and they'll post it to YouTube.